Okay, so now we're ready to get into some of the nuts and bolts of differential equations. So let's start out with the question to be or not to be, right? So let's start with this differential equation dy dx is equal to 2y. So that's looking at how fast y is changing with respect to x, and we have that set equal to 2y. So the rate of change of y depends on how big y is, and this factor of 2. This is a more compact way of saying it. I think it's less useful as we go to actually solve differential equations, but you will see that in the textbook. Don't be confused by that. What I would do whenever I see this in a problem that I'm trying to solve, I usually just rewrite it as dy dx. It's more informative of what is changing and what it is changing with respect to. So I prefer that notation when working with differential equations. Now, when we look at this, okay, right now we have y as kind of written, we have y and x as our variables, and that's because we're going to probably plot y on this axis and x on that axis. This is just generic. In some of our previous examples, instead of putting y over here, it might be temperature and it might be time over here. So we could have dt with respect to time. I better be careful. The derivative of temperature with respect to time. It's confusing if I use too many t's. Or we could have the amount of something as a function of time. So y is just generic for output. X is generic for the input variable. And so we're going to just talk about dy dx generically as we move forward. But remember, y could be representing all kinds of things. And more often than not, actually, when you're working with differential equations, x is replaced by time. So let's continue onward. Okay, so we have this equation. Let me just rewrite it. Dy dx equals 2y. And I want to show whether things are solutions or not. That's what the to be or not to be. Okay, so let's just go back in your math world a little bit. And let's say you had the equation y equals 2x plus 4. And I'm supposed to show that the point, let's say 1, 6, is a solution to this. Well, how would I do that? I would substitute 6 in for y, and I would substitute 1 in for x, and sure enough, I get that 6 is equal to 6. I could, however, show that, let's say 2, 7 is not a solution, all right? Because if I start with 2, 7, I'd have to write 7 is equal to 2 times 2 plus 4, and 7 clearly does not equal 8. So if I try to say that 7 equals 8, this leads to, I can say 7 does not equal 8. Let's actually change that to an equal sign. Oh, sorry. Equals. This leads to a patently false statement, whereas this leads to a statement that will be true all the time. So we can say that 1, 6 is a solution to y equals 2x plus 4, but 2, 7 is not a solution to that. Now, it turns out the solution to differential equations are functions, or they often are. Okay, so let's look at a couple possibilities. Let's consider y equals, what do I have here? E to the 2x. I want to consider that as a solution. Well, if I'm going to use this as see if it's true, I need to be able to substitute this into the equation that we have here. Well, I have something to put in for y, but I need something to put in for dy dx. So in order to prove that something is a solution to a differential equation, we need to take derivatives. So this is an excellent chance to review a quick chain. Okay, the derivative to that would be 2 e to the 2x. All right, now we have a y and a dy dx. We can substitute, so say sub, and we have that 2 e to the 2x, that's dy dx, has to equal 2 times e to the 2x. And if you look at that, those two sides look identical, except for the parentheses. So no matter what value I put in for x, 2 times e to the 2x will equal 2 times e to the 2x, or x equals 0, 1, 2, 3, 4, negative numbers. You can put in irrational numbers. This is always true. So I can put a check mark. So y equals 2 to the x is a solution. All right? Now let's consider y equals 2e to the x. Let's look at that. Okay, so what would dy dx be? Dy dx would simply be 2e to the x. Now let's go to the differential equation, and we would substitute. So all right, we're going to sub, the left side would be 2e to the x is equal to, on the right side, have 2 times 2y, which would be 2e to the x. So I substituted in for dy dx and for y. And if you look at this, I know obviously let's just do a little bit more algebra here. 4e to the x. 2e to the x does not equal 4e to the x. In fact, there are no values of x that would make this true. So this is a false statement. That is false. Therefore, we can say, going back to the top, we can say this is not a solution. Now, here's an interesting thing. Is y equal e to the 2x the only solution? Okay, this is a little bit like quadratic equations. They have more than one solution. We're going to see there's another solution here. In fact, let's put in y equals 3e to the 2x. Just quickly, dy dx with a quick chain, 6e to the 2x. All right, so we substitute into our differential equation. 6e to the 2x is dy dx is supposed to equal 2y, 2 times 3e to the 2x. All right, and sure enough, 6e to the 2x equals 6e to the 2x for every possible value for x. Now, an important thing here is it must be true for all x. Not just coincidentally true at one value of x. This must be true for all x to say that y equals 3 times e to the 2x is a solution for all x values. All right, so that is a solution. Let's consider another one. What about y equals e to the 2x plus 3? Maybe throwing on a constant won't matter. E to the 2x was a solution, so maybe adding 3 on will still be a solution, because when we take the derivative, the 3 will go away. So we know the derivative of this will be 2e to the 2x plus 0. So now let's substitute into the differential equation. We get 2e to the 2x on the left equals 2 times y, e to the 2x plus 3. So this comes down to 2e to the 2x equals 2e to the 2x plus 6. Which is clearly going to be false. No matter what value you put in for x, you're going to have the 2e to the 2x parts on each side being the same, and we're going to have 6 more on the right. So this is clearly a false statement. Since this is a false statement, we can say that y equals e to the 2x plus 3 is not a solution. Okay, so quick review, there can be more than one solution. In fact, it looks like if 3e to the 2x worked nicely, maybe other things times e to the 2x could work nicely. There might be an infinite number of possible solutions to this problem, all right? But they're all going to be similar to each other. There are also an infinite number of functions that are not solutions to this differential equation, and we can see a couple of those to the right. Let's look at one more of these. Okay. In fact, let's look at our example about the coffee cooling. So let's start with the rate of change of temperature was negative 0.05 times T minus 20. Okay, so let's start with a guess. T equals 80 e to the negative 0.05 t plus 20. It wasn't a guess. I know what the answer is. So Let's see what happens when we allow t to equal that. Well, to see if it's a solution to the differential equation, we're going to need to know what the derivative of the temperature with respect to time is. So let's find that. Okay, so we're going to get a lot of practice taking derivatives in this homework. All right, so notice there's a constant of negative 0.05 in front of the t. So when we take the chain rule, we will multiply by negative 0.05. And so we'll have a negative here. Oops, let me switch back to black. Negative and 0.05 times 80 should be 4, I believe. Let me just double check that. 5% of 80, yes, that would be 4. And then we have e to the negative 0.05t back again. Okay, so, and then the derivative of the 20 is 0. So negative 4 e to the negative 0.05t is in fact the derivative of temperature with respect to time. If you need to, write the chain rule out more fully in your little grid format, but that was just, it's a quick chain where you multiply by the coefficient in front of the variable there. Okay, so that is a derivative. Let's substitute in. So negative 4 e to the negative 0.05t should equal negative 0.05. Okay, then we have to put in the whole equation for t, 80. When I substitute something with multiple terms, I should put it in parentheses, 80 e to the negative 0.05t plus 20 minus the 20 that was in the original equation. Well, we just took 5% of 80 and saw that it was was 4. So negative 4 e to the negative 0.05t ends up equaling negative 4 e to the negative 0.05t. The 20s cancel. This is true for all possible times. Okay, so at all times, this will in fact be true. So we did find a solution. So this is, I should maybe box this in. This is a solution. This is true. Therefore, what we picked for t is a solution. All right. Let's go back and look at one that is not a solution. Okay, so let's just try, what if we had tried t equals negative 0.05t plus 20? Well, that's nice because the derivative is easier to take. That's the derivative. But we can clearly see if we substitute into the equation that negative 0.05, if we try to set that equal to, let's see, negative 0.05 times negative 0.05t plus 20 minus 20, the 20s cancel, but negative 0.05 does not equal, that would be negative 0.0025, I think. Doesn't really matter if I was off. Oh, and it's positive now because we have a double negative times t. So something, this clearly is false. In fact, I believe it's false for every value of t. I don't think there's even a value of t that would make this true. All right. Oh, no, there is one value of t. It would actually be a negative value of time that could make this true, but it's not true at all times. All right, so it needs to be true for all input values of t in order for what we had up here to be a solution. We're assuming it's a solution for all t in the domain. So this is not a solution to the differential equation. All right, it would be pretty easy. I'm not going to work through this, but it would be pretty easy to show that 60 e to the negative 0.05t plus 20 is also a solution. The work for that would be exactly like it was when there was an 80 there, and we would see that it works out to also be a solution if we tried that.